Today I am going to start with special theory of relativity. So, introduction. So, what is it and why we needed to go to special theory of relativity? Like before the Einstein arrived, like in Galilean transformation or in Newtonian transformation, you can see that the universality of time is always implicitly assumed. Like there is no transformation for time, like t is equal to t prime in all transformations. So regardless of inertial frame, whichever inertial frame of reference it is. So but one thing which Einstein observed was that this implicit assumption was invalid when the quantities involved are nearing speed of light, or I can say they are comparable to speed of light. So that time these does not give the correct results. So he came up with a special theory of relativity in 1905, which was only applicable to inertial frames of reference. And then after 10 years in 1915, he published the general theory of relativity, like that is applicable for even non-inertial frames of reference. And also it redefined the term of gravity. So let us not discuss that, but for today how we will discuss about the postulates of special theory of relativity. And what are those two postulates? One is that the laws of physics are the same in all inertial systems. No preferred inertial system exists. So we can see that this is called as principle of relativity. So the second postulate is that the speed of light in free space has the same value c in all inertial systems. So this this is called as the principle of constancy of speed of light. So as we have seen in Newtonian relativity, like when we relative velocity, we cannot have the quantities, like we cannot have the quantities which are greater than speed of light. So c plus v kind of speeds does not exist. So these that's why we have to find new transformations. Later on we will see that these new transformations were called as Lorentz transformations, which are used for relativistic speeds, like which are speeds for which the they are comparable to speed of light. So let us keep that for one more day. But I am just giving that in relative velocity concept, which we study in high school or anywhere, Newton's laws, Newton's physics are not applicable here at these speeds. So this, according to this postulate. So and also one more thing, it states that all reference frames are equivalent. So this is the first postulate. There is no preferred reference frame, like all frames are equivalent. So if we can take the example of train moving with the constant velocity v, and its velocity is measured with respect to ground, assuming that the ground is at rest. So now these are both are this is an equivalent, but actually we can think that ground is not at rest. That is, it is the earth is rotating and revolving around the sun. So these effects are not observed every time, but in a particular cases it is observed, like Foucault pendulum experiment. So that you may know about it before. So now the second postulate, again it states that the classical velocity addition theorem is does not apply when the speed of light is involved. That is, we can think that no real world speeds are greater than speed of light, or c plus v form. So now we have to find a way uh, to define the universal time scale, and we also must be able to give some meaning to what is the meaning, what is independent of frame of reference. So what does it means to be independent of frame of reference? So we'll consider, for example, let us consider two events as shown. Two events, uh, then what happens is, if we take the two events are occurred at same time, then this statement can be thought as three cases. Case one is that we can consider that two events have occurred at the same place and and single particular frame of reference. So this is case one. Like, we can assume that events A and B exactly occur at the same place in one particular frame of reference. And the case two is nothing but when events A and B occur in different places in same inertial frame, and also it is observed, they are observed from same inertial frame. So only one inertial frame is reference, one inertial frame of reference is involved in case 1 and case 2, but the event occurs in case 1 it occurs at same place, but case 2 the two events occur at different places in a same inertial frame. But the case 3 is the most interesting one. If we come case 3, what happens is that when two events A and B occur at different places in the same inertial frame of reference, but these occurrence of events is observed by different inertial frames. So this is the most interesting case out of all three, and why we will see. Uh, so these are the three cases. So if I want to show you pictorially, so this is the case. So this one, so two events occurring at the same place, same time, like time is t equal to 0 and events. This is simply overlapping each other. This is shown as in the Venn diagram form. But yeah, then case two is different places, but at same time in same inertial frame of reference. So yeah, you can see there is some distance between these two. So different places, but it are observed. Event is occurring in one frame of reference, but it is observed by other frame of reference observers as well. So these are the three cases. So now we can do one thing. Uh, so we have to first, before measuring when the event occurred, for example, we have to know that we have to ensure that clocks are synchronized, because one cannot measure differently, right? So we can assume we have to find a way to make sure that whoever is measuring their clocks should be synchronized with each other. So uh, we have to think of observers who are measuring the events have the clock synchronized with each other. So this we have to be there. So now the question is, like, what is the question is how to synchronize? How to synchronize? So this question is very interesting. So how to synchronize the clocks? So what happens? So if we take one case, uh, like if we take one case of a moving train with velocity v, with some clock having some time, or say some time, and also it is passing to the station at the same time, which has a clock placed in the station, and both the trains both the train and station clocks read the same time, or vice versa. So we can say that the two clocks are synchronized if the time in the station and time in the train are same for observer from train, and also those who are observing from the station. So this is a scenario, like pictorially if I want to represent. So this is a scenario here. We can see that a train is moving with some velocity the platform, from the platform in the station. Here it is 2:15. Like both the clocks should have the same time, and the observers should note that the person who is in the station is also able to see the time 2:15 in the clock inside the train, and the person who is inside the train is able to see the time of 2:15 in the station. No, this scenario might look like, oh, what is there in this? This is very obvious, right? Because we think that every day we see it, and how the time of the two clocks can be different. Or sometimes we use the railway clock uh, to set our own clocks. Like this is just sometimes we do it because it runs in more. It is more precise compared to our clocks, and our clocks lose time. Like those are the different topics, but uh, just we do it. But here, if we can you imagine a scenario before proceeding? Like I want to you to imagine a scenario. If you what if you are in the train and you see some time, you see time differently compared to the station. Like is it possible? But my answer will be in relativity it is possible. So let us see how it is possible. But before that I am telling you that it is possible. Like both the observers, if I am sitting in train and I'm just seeing the clock, then it might show me a different time compared to what the person sitting in station is seeing. So reading the value. So these kind of things happen in relativity. So how? So let now we are going to touch upon the concept of synchronization. So why it is actually the everyday method of synchronization is incorrect. So why? Because we consider that light takes no time to reach us. So that is what an implicit assumption which we take, that when we assume that clocks are synchronized. But when times are comparable to the speed of light, for example, not time, I mean that time scale, speeds are comparable to the speed of light, then we can take that it is not the case. Like even the small time becomes very significant. Case one of two events occur at the same place. Like as I have shown the three events, like first case is simple that both occur at the same place in the same inertial frame. So I can think that okay, A and B both are occurring in the same place. So both clocks have the. I assume that both clocks have eyes and they could see the clocks internally. They can observe that same nature. So similarly, when the clock of event A looks towards the clock of B, then it finds both have same readings because they both are at the same place. So it will light will take no time, in 0 seconds it will reach. So it is like that. So we can think that the two events are simultaneous. So now we go to one more case. If we go with a case two where two events are separated by some distance. So this is event A here and this is event B, and they are separated by some distance L. Then we can think that distance of clocks is also L. So if we take how much time it will take. If for example, so light will take 2L by C time to reach event A and from event A to B and then come back, right? So it to come, go and come back, it will take 2L by C. So it will have to travel twice the distance. So so what I can say is that if event A occurs at time t, so this occurs at time t, then according to clock of A, then the clock of B reads the event time as t minus 2L by C. So this is very reasonable assumption. So this is not assumption, but this is a calculation. So we can see and vice versa. If we take even with respect to event B, it is exactly opposite. So thus two clocks measurements are lagged by 2L by C, but we cannot have two observers of same reference frame to disagree upon the synchronization. There is a lag, but both the clocks will agree that they are synchronized. So this method is flawed in itself here. So why this method is flawed, we will see. So there is one more method which is used to calculate there's a better way to uh, how the synchronization happens, and that we are going to look at the uh, that we are going to look in the next video, like how we will look into the case scenario, how the what is the actually, whether event is simultaneous, or how what is the synchronization concept completely. We will look, and then we will come up with some conclusions, and we will see in the upcoming video. Thank you.